So welcome again. Here we are, session 5, truth tables, tautologies, contradictions. Okay, so we talked last time about logical operations and how we can describe logical operations by truth tables. And today we will practice using truth tables more on everyday language. We will practice more to translate sentences from English into logic, into a logical expression, formal expression, and back. And we will talk about tautologies, contradictions, contingent, consistent, and inconsistent statements and what all these words mean. Okay? So first let's practice translations a little. You remember I said many times already that this whole thing only makes sense if you actually do the exercises. So you should please now go get a piece of paper and get a pen and sit down quietly somewhere where you can actually work and do these exercises. Don't just sit there and listen to this like a TV show, because then you will not learn anything, right? You can easily read the whole thing in the PDF file, which I have given you in Moodle. But the point is to actually do these things. So you should now really take an hour of time and sit there and do these exercises. This is how you will learn best, okay? So we begin with a few translations. Translate this into a symbolic form. Symbolic form in this case means, you know, the formula with the propositional logic calculus, right, where you have the propositions as letters and then you connect them with these logical operators. So translate: if and only if this tree gets enough water and sunshine and it is not too cold, it will grow well and give fruit. Okay, this is an easy one just to warm up a little and to remember the logical symbols. Okay, so try to write this down as a symbolic expression. Stop the video here, do it, and then come back. Okay, so you did this. Remember that the first thing you have to do is to always write a list of the letters you use. This is in the exam, you have to do it so that I can see what your letters mean. I'm not going to try to decipher your expression and do this myself. I want you to tell me what your letters mean. So always make this list. It's also good for you because then you avoid having the situation that you use the same letter multiple times, right? Which would be a mistake. Every letter in such an expression has to be used to mean always the same thing. So you can use a letter multiple times, but then it means the same proposition. Sometimes it will be confusing. You might have multiple propositions that seem to begin with the same letter and then you just reuse the same letter, and this would be a mistake, right? And so this is why making such a list in the beginning lets you avoid this mistake, right? So make a list like that. W, the tree gets enough water, right? W for water. S for sunshine. C for it's too cold. G for growing well. And F, it will give fruit. And now you can use these letters to write down your expression. If and only if, obviously, is a biconditional. So this has to be translated as a biconditional. And then you have the two sides of this biconditional. On the one side, you say if it has enough water and sunshine and not too cold. And you have to remember that the not is a logical operator. So it goes out of the proposition C, which means it is too cold. So you don't have a proposition saying it's not too cold. You have a proposition saying it is too cold, and you have a negation of this proposition, right? In logic is always like this, the not always goes out of the proposition. And then you have the if and only if, and on the right side of it, the tree will grow well and it will give fruit. So this should be very easy, right? There is nothing complicated here about that. Okay. Let's do one more. The school has collapsed, but it is not true that 5 students died. A cheerful little exercise. So try to do that one. Okay, so we see this is very easy, right? It looks like it might be complicated in some way, but actually it is just two propositions. The school has collapsed. As 5 students have died. D. And this is not true, so not D. Okay, so this is another way of expressing the not in English. I could say 5 students have not died, or it is not true that 5 students died. This means the same, right? It means it's exactly the same thing. In logic, it is in both times, it's not D. Okay, if you want to go, then I will go with you if it is sunny. So this one is a little more tricky. Try to think about it for a moment and stop the video and then write it down and return when you have an answer, and then we can compare it. Okay, so here we go. Y, you want to go. I will go with you. And S, it is sunny. And now we can put these things together. You could say, if you want to go, this is the first expression here, right? If then is an implication. So if you want to go, then, if it is sunny, then I will go with you. Right? Make sure that you have the right sequence. It's not like you're saying, if you want to go, then if I want to go, then it will be sunny, right? Although the sunny is the last thing in the English sentence, it is not the last thing in logic. It is the condition for me going with you. It is not the consequence of it. So it has to be translated in this way with two implications. Or you can also change things around a little and realize that the two conditions have to be true at the same time. You want to go and it is sunny. And so I can just take these two conditions and put them together with an and then have one implication that gives me the result. So if it is sunny and you want to go, then I will go with you. Right? Whether Peter is coming to the party or not, Mary is not going to come to the party. So try to translate that. Stop here for a moment, do that, and then we talk about it. So there are multiple ways to do this, right? You can say P means Peter comes, M means Mary comes to the party, and then I can say P or not P implies not M. So Peter comes or Peter doesn't come. If Peter comes or Peter doesn't come, then Mary will not come. Now you could realize that this is a pretty complicated way of saying that Mary will not come, because actually it doesn't depend on Peter at all whether Mary will come or not, because she's just not going to come. So this is logically equivalent to what is down there, not M, right? Peter doesn't actually matter in this sentence at all. So you could say this is equivalent to just simply not M, but this wouldn't be a good translation because the sentence actually does talk about Peter, right? So when you have an exercise like that which asks you to translate something, you should try to stick closely to what the actual sentence does, no matter whether it is logically perhaps equivalent to something else. So if you say not M, it is logically correct, but it will not give you the full marks because it is not a good translation. You can also do it more complicated. You can try to unpack this a little and say, if Peter comes, then Mary will not come. This is in the middle solution here. And if Peter does not come, then Mary will also not come. Then you get this expression number 2 here, right? So this is, again, the same, is also equivalent. So you see that it is often possible in logic to have different translations of the same sentence, to have different ways of expressing it in logic that are logically equivalent, right? There are always many ways to write the same thing in logically equivalent ways. Now we want to make a truth table to see whether these things are actually equivalent. I mean, I can say they're equivalent, but you don't have to believe me. If you want to see if they're actually equivalent, you can try it yourself. So take these two expressions, the long one, P implies not M and not P implies not M, and take simply not M and try to prove that they are logically equivalent. Try to do it yourself first, and then I will show you how it works. Okay? So how do we do this? The key here, when you want to do something like this, is to realize if you want to show an equivalence with a truth table, you need to put both things into the same truth table. This is the most important thing. Because if you make two truth tables, one with the first expression, one with the second, they won't even have the same number of lines, right? Because the first expression has two variables, so it will have 4 lines. The second expression has one variable, so it will have 2 lines. How do you compare these? You cannot compare them, right? if you want to compare two truth tables and see if you have the same values, they need to be the same truth table. Okay? So you put both into the same truth table, then you would make a truth table, which I don't have here, but we can talk about it if you want in the tutorial session. So what you would do is to make a truth table with P, M, not P, not M. Write down, calculate all the columns, and then you compare the column for the first expression with the column for the second expression. And if they are in every line exactly the same, in the same order, this is why it has to be the same truth table, because if you take a different truth table, you might have different order of the results, right? Depending on how you fill your variables. So it's important to have the same truth table, and then you can compare the first expressions column with the second expressions column, and if in every line it is exactly the same order, same results, then the two are equivalent. Okay? I think you can do this yourselves, right? It's not that difficult. Okay. So now this is a little more complicated still. So we go from the easy to the more a little more demanding. Unless you try to improve yourself and unless you improve your attitude, you are not going to succeed. So this is a little difficult with the unless, right? You have to think for a moment, what does unless actually mean? And then try to translate this in some way, right? So let's do it. Stop the video here, pause it, and do that, right? So here we are. Y, you try to improve yourself. A, you improve your attitude. S, you are going to succeed. Again, you are not going to succeed is the negation of you are going to succeed. So your proposition is S, you are going to succeed, and then you have a logical operator not in front of that, right? And there are three possibilities here. You might have one of the three, or you might have something else entirely that is either wrong or right, because there are many more ways to write it in equivalent ways. So the first one is perhaps the easiest to read, where you say, if not, so the if then is the arrow, right, is the implication. And then we are on the left side now, not improve yourself and improve your attitude. So if you do not improve yourself and improve your attitude, then you are not going to succeed, right? This is the most straightforward translation. But you can also say, which is logically equivalent, if you improve yourself and you improve your attitude, if. Now the second one would be you improve yourself and you improve your attitude, or you are not going to succeed. Right? This is, if you think about it, this is equivalent, right? You improve yourself and your attitude, or you don't succeed. So you have to choose, the one or the other. Or you can also take the one on the right, if you succeed, then you have improved yourself and your attitude. Because if you had not improved them, you would not succeed. So if you succeed, you know that you have improved them, right? This turns the thing around, but it is equally correct. Makes sense, and you can also write that. And of course, there are many ways how you should not write it. For example, the last expression on this page, Y and A implies S. This is something different, and it is wrong. Because if you say if you improve, this would mean if you improve yourself and your attitude, then you are going to succeed. But this is something different. This is not what the sentence said. Because the sentence said, if I don't improve, I will not succeed. This does not mean that if I improve, I will succeed. I might improve and still not succeed because of some other reason, right? So you cannot this turns the implication around, right? And this is not what you're supposed to be doing. Okay. So the unless not, let's see it in another example. In order to stay alive, you need to breathe, to eat, and to drink, right? You need to breathe, to eat, to drink. So it's correct to say, unless you breathe and eat, you are not going to stay alive. This is true. But from this now, you cannot conclude that if I breathe and eat, then I'm going to stay alive. No, I'm not, because I also need to drink, right? So if you breathe and eat, you will stay alive is not true, although unless I breathe and eat, I'm not going to stay alive, right? Because I have three conditions. If I fulfill two of them, I'm not going to stay alive because the third is not there. But if I don't fulfill two of them, I will fail to stay alive, right? You understand this? So you have to think about that a little. Take your time. I mean, that's the point of the video, right? You can go back and just watch it again until you can be sure that you have understood it. Now, back to the truth tables. You see here the truth tables for the basic logical operators. You see the and, the or, the implication, the biconditional, and the not. And these you have to memorize. There's no way around that. You need to know these 5 logical operators, how they work and what their truth tables are. And as we said, the and, the or, the not, and the biconditional are relatively easy. The only tricky one is the implication, and the implication you have to memorize. Don't ask me why it's like that. It is like that, whether you like it or not, and you have to learn it like that. And because many of you fail to memorize the implication, this is why when we have exercises or exams, we always ask for the implication, so that, if you don't know it, you will have a problem. So make sure that you memorize the implication truth table. Okay, so all these you should be able to write down like that, because only then can you use this to calculate more complicated expressions. So now, how to build a truth table? Again, I have a different way today from last time. Last time I explained it in another way, now I explained it in a different way, so that we increase the probability that the whole thing sticks eventually. So let's take an example. If the weather is fine and I don't have to work, I will go to the park or to the beach. The first step is to write this down as a symbolic expression, as a formula. It is an if-then. If it's fine, then I will go to the park. So this tells you we have an implication, not a biconditional. It doesn't say if and only if, it says if. So it's an implication. And the rest is easy, right? Fine and not work, then park or beach. You can read this down there, right? This is an easy expression. So now, how to build a truth table for that? I have 4 variables. F, W, P, and B. So with 4 variables, how many lines do I need to have in my truth table? How many lines does the truth table have? If I have 4 variables, I have 16 lines, right? Because one variable has 2 values, 2 variables have 4 possible combinations, 3 variables have 8 possible combinations, and 4 variables have 16. So now I have my 16 lines in the truth table, and I start filling in the top line first. I have my variables F, W, P, and B, and then I need some more. So I take the sub-expressions, right? I need some more. I need a not W here, and then I need the F and not W. I take them apart so that I always calculate only one operator at a time, right? So now I have F and not W, then I have the P or B, and then the F and not W implies P or B. I have already calculated the parts, so the last expression is only the implication that I have to calculate. So you always try to take it apart in such a way that you have to calculate only one operator at a time. So how many lines do I need again? The non-mathematics answer, insert T and F until all your variables go from true, 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 true to false, 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 according to the pattern that I explained to you last time. Or you can say the mathematical answer 2 to the power of n, where n is the number of variables, which means propositions in your expression, right? That is, 2 variables would be 4 lines, and 3 variables would be 8 lines, and 4 variables would be 16 lines. 5 variables would be 32 lines, but it's unlikely that we will ever ask you to do a truth table with 5 variables, because 32 lines is too much for an exam, right? So this normally will stop around 4 lines. Okay, so how do you build the truth table now? You remember I told you to use a trick. Don't try to guess randomly, how to put the values there. You start with any variable you like. It doesn't matter which one you take first. Just take any one and begin with true, false, true, false, true, false, true, false. Go your 16 lines from top to bottom. Then you take the next variable. Again, it doesn't matter which one it is. Here now I took the rightmost one. You can start with the leftmost one. This is irrelevant. But now the trick is to use steps of 2 instead of 1. So instead of going true, false, you go true, true, false, false, true, true, false, false, and so on. Now you can easily see that this gives you all the combinations of these 2 variables. And you can see the combinations in the first 4 lines. If you just look at the first 4 lines until here, you will see that now we have all the combinations of these 2 variables. We have true, 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 false, false, true, false, false. Okay? And this repeats. And now I do the same with the next variable, but with a step of 4. So I have 4 true, 4 false. And again, you can see that in this way, I get all the possible combinations 2 times. So after 8, it would be okay. After 8, they repeat, right? 8 lines are unique, and then 8 lines repeat. And this is necessary because I still have one variable, which will go 8 true and 8 false. And by doing that, now I get all the combinations of all the variables. Okay? So if you have any trouble with this, just make sure that you memorize it. Go back to the previous presentation where I explained it again. And just do it like that. Don't ask, why or can I do it in a different way. You cannot. This is the easiest. This is the best way to do it, the fastest. So just do it like that, okay? So now you have not W. Not W obviously is the negative of W. So whatever you have as a W in your truth table, now you take the opposite. Instead of true, you write false, and instead of false, you write true, and then you get this for not W. Then again, use your fingers, right? Put your fingers on these columns to know where you are, and then walk down here with the finger pointing, at the column so that you know what to fill in the other column that you're just calculating. So F and not W. Put one finger on the F, one finger on the not W, and then go down here and try to calculate the result. Then AND is false if one of the variables is false. So the first 4 lines will be false. You can already see the next 4 lines will be what? In our result, they will be true, right? And what about the rest? The rest will be false, right? Because there's always the F false now. It doesn't even matter what the not W is. Okay, then we have P or B, again the same, P or B. Because it's an or now, it's true if any of them is true, and only false if both are false, right? So you get the first 3 lines are true, because there's always one of them true, and only every 4th line has false, false, and therefore the or will also be false, right? You do it like that. And then finally we are finished. Now we have only the implication to calculate. Now you remember that the implication, if you don't remember it, then you have a problem, go back. The implication is only false in one case, where the first part of the implication is true and the second is false. And this is only the case in one line. You see the one red line there in the middle. Or in all other cases, it is true. So that's the truth table. This is false under one condition and is true in all other cases. So you should really know how to build a truth table now, and you need to remember these logical operators and their truth values. And now do another exercise. Calculate the truth table for, if it is hot, I will go to the beach and swim or surf. Right? Try to calculate this truth table now. And do it yourself. Stop the video here. Come back in a moment. Okay, so here we are. This is the expression. If it is hot, if then, so it's an implication. If it is hot, then beach, B is the beach. I will go to the beach and swim or surf. Again, swim and surf both begin with S, so there's a trickery here. If you are not careful, you might say S or S, right, for swim or surf, which would be wrong, of course, because inside the same expression, the S can have only one meaning, so you need to say F for the surf or some other letter but not S. And your truth table, I didn't want to paint the whole truth table here again because it's pretty tedious with a table function to make these truth tables. But your truth table has 11 true and 5 false lines. So count your falses and your truths, and it has 16 lines obviously, right? So if you come up with 11 true and 5 false, then you are fine. So how to calculate the truth table? First time you write down your symbolic expression on top of it, then you write your 4 variables, or whatever many variables you have, then you write the sub-expressions, and then you go with this trick of true, false, and then double step true, false for the next variable, and then again double 4 times true, 4 times false, and then 8 times, and so on, until you have covered all your variables, and then you calculate one by one the columns. Don't try to go in lines. Go like we did it in columns. If you try to calculate one line from left to right, it will take you forever, because for every column you would have to do a new operation. And your brain doesn't like to switch the operation. Every time you have to do a new operation, your brain has to reorient itself. It has to look again at the variables. It has forgotten what it is doing. And it will take you forever. So the best way is to do one operation on all lines. So stick to one column and to all lines. And then go to the next column and to all lines. This is how your brain can do it fastest. Of course, in principle, it doesn't matter. If you were a computer, you could do it either way. But you are not, right? So your brain works best if it does the same operation on different values. This is easiest for your brain, right? So therefore do it like that. Okay, now finish with the truth tables for the moment. We will still use them later, but this was the whole explanation. We don't explain more truth tables. I hope that you know enough now to get your truth tables right. So now, tautologies and contradictions. Let's look at these sentences here. All daughters have a mother. All ships are ships. Bananas are either sweet or not sweet. These sentences, if you look at them, they are true, right? All daughters have a mother, all ships are ships, bananas are sweet or not sweet. But they're not simply true. They are something more than simply true. They are necessarily true. They could never be false, right? This is different because I can hold up this pen here, show you this pen, and say this pen is a red pen. This is also true, but it's not necessarily true. This is a red pen, but it could well also have been, like perhaps this here, a black pen, right? It's not necessarily a red pen. So there's a difference between something being necessarily the case and something just happening to be the case. The wall behind me is white, but it's not necessarily white. I could have a blue wall or a green wall. While all ships are ships could never be different. Bananas are sweet or not sweet. This could never be different. No banana can be anything but either sweet or not sweet, right? There's no other way how this could be. So this is wait a second, I need to turn on the electricity because otherwise we will soon be out of power here. You see that these are necessarily true, right? And these are called tautologies, logical tautologies. They are statements that are necessarily true. They can never be false for purely logical reasons. For example, bananas are sweet or not sweet. You can see this yourself with the truth table. As or not as. Try to make a truth table of this, and you will see it has 2 lines. As can be true or false, and not as can be true or false, and then you can calculate as or not as, and you will see that the truth table shows you this is always true. There is no way to make this expression false ever, right? The opposite of a tautology is a contradiction, is a sentence which, for logical reasons, is always false, right? That's a contradiction. For example, my car is big and small, where small is meant to mean not big. If I say this, be and not be, then this is a contradiction. Again, make a truth table if you like. You will see that this is always false. It's a good exercise. If you have time, stop here, make a truth table for that. It will take you a few seconds. You will see that this is always false. Now, every statement which is neither a tautology nor a contradiction is said to be a contingent statement. This contingent, the word contingent, just means it's not necessarily true, it's not necessarily false, it is something that can be true or false. Contingent statements are true or false, depending on the truth values of the propositions which compose them. And every normal statement is a contingent statement, right? So most things you say in everyday life, this pen is red, is a contingent statement. My name is Andy is a contingent statement. It can be true, it can be false. This bottle of water is full is a contingent statement, because in a moment it will be empty. Okay, so that's it. Now, we can use truth tables to show that some statements are tautologies, always true, because you see this in the truth table. If the truth table has all true, 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 then it's a tautology. Or you can show that it's a contradiction. The truth table for the expression is always F throughout. Or contingent means that your truth table has sometimes true, sometimes false, right? So try to show with the truth table whether the following statement is a tautology, a contradiction, or a contingent statement. Just make a truth table for that and find out what it is. Stop here for a moment, do that, and return when you are done. So if John marries me, I will be happy, and if he doesn't marry me, then I will not be happy. Here comes the solution. Marry implies happy, and not marry implies not happy. This is contingent because some lines in the truth table are true, some are false. This is actually equivalent, of course, to marry by conditional happy, right? So if he marries me, I will be happy. If he doesn't marry me, I will be not happy. So I will be happy if and only if he marries me, right? M by conditional H. And this is a contingent statement. Okay, now don't confuse contingent with consistent, right? The logicians have gone into great trouble naming all the things similarly so that students get consistently confused. Consistent is different from contingent. Consistent is a property of multiple statements. One statement cannot be consistent. Consistent is a property of more than one statement together. Multiple statements together can be consistent with each other if they can be true at the same time. That is, if it is possible for them to be all true together. A set of statements is inconsistent if it would be impossible for them all to be true at the same time. And don't confuse consistent with contingent. Two totally different things, right? Sound similar, but they're totally different. Consistent means they can be true at the same time. Contingent means one statement can be sometimes true, sometimes false. Now, an example for consistent statements. C, I'm in class now. H, I'm hungry now. P, I'm at Pacific Place now. C and H are consistent. I can be in class and hungry at the same time. Although it doesn't have to be true, but it can be true, and that's the point, right? They are consistent means they can be true at the same time. It doesn't say they are necessarily true at the same time. They might be not. H and P are also consistent. I can be hungry at Pacific Place. But C and P are not consistent. They're inconsistent because I cannot be in two places at the same time. Right? Easy to understand, I hope. Make sure you understand that. If this was too fast, then, just stop the video and we'll go back a few seconds and listen again to that. Okay, so what do you think of this? Are these statements consistent? I will go to the cinema tonight. Second, if I don't go to the cinema tonight, I will not eat rice tonight. And I don't eat rice tonight. Are these consistent or not? So use a truth table and show whether these are consistent. Okay, I will go to the cinema tonight is C, let's say. If I don't go to the cinema, I will not eat rice. Not C implies not R, and not R, I don't eat rice. And then you make your truth table and you see, you write down all these statements and you see, is there a line in which all three can be true at the same time? And you see in the second line, your three statements you're interested in, C, not R, not C implies not R, they're all true at the same time. This means they are consistent because they can be true at the same time. Again, stop the video, look at the table if you like. So what happens here? If I change the statements a little, if I say in the second statement, if and only if I don't go to the cinema, I will not eat rice tonight. That's the only difference. Instead of if, now I say if and only if. show if these are consistent. Stop the video again. In a moment I will continue. Okay, so now the only difference is the second one has a biconditional instead of an implication. And now if I make a truth table, I can clearly see there is not a single line in which the three red statements that are here highlighted in red, these are the ones I'm interested in. The others, R and not C, are just helper columns which will calculate something which I need to know, but they are not the answer. They are not the statements I'm looking at, right? So I have to look at the red statements, which are the ones I'm asking about. And I see that there is not a single line where they are all three true together. There's always one of them false. So this means they are not consistent, they are inconsistent. Okay, so that's it. Do you have questions about these things? Then please write down your questions now, because often you forget the questions later. If you have a question spontaneously, then it's good to record it, write it down, and later either send me an email or, even better, ask me in the tutorial session for this, which we will have using Zoom, like we did today, like we will do tomorrow, three days a week, right? We have our Zoom sessions in which you can ask me questions about these things. So please record your questions and ask me later in our online tutorial session, right? So you will find some exercises down here also. Translate into symbolic form. You have some answers here and explanations of what can go wrong. You have a little discussion about meat or fish balls. This you remember we had in the previous session already. We had this thing with not meat or fish balls, and what it means, and whether you put the not inside or outside the brackets, right? So this is a little tricky. It's okay if you are still confused about that. We talk about it again next time. Presentation 6 has another session on this, on the use of not together with brackets and or, and I will explain it again, so don't worry about that too much. Then you have a little more crazy translation exercise here. You can do it. Again, don't look at the answer before you do it, right? And then you have a little exercise comparing truth tables, and that's it. So you can do these exercises at home. You find them in the written in the PDF file, right? Do them yourself, or we can also talk about them again in the tutorial session when we meet virtually in the tutorial session for your class. Okay, so today what did we learn? We are at the end, right? We practiced more using truth tables. I explained again truth tables, and then I explained tautologies, contradictions, contingent, consistent, and inconsistent statements. Make sure you know what each one of these is, and don't confuse them. Especially don't confuse contingent with consistent, because, you know, again, obviously these are the things we ask you in the exam, right? There's nothing more that we can ask you. You can ask you questions like that, and there will be probably some kind of question that will ask you to distinguish these things correctly. And so if you confuse them, this is obviously not so good for you, right? Okay, so that's it. I hope we are happy with that, and thank you for the moment. If you have questions, either write me or ask me at the tutorial session. Here is my email address, okay? So thank you, and see you next time.